everybody. Thanks for listening to this Acids and Bases Complete Curve Analysis lecture. And it's to go with the experiment in your laboratory manual, Acids and Bases Complete Curve Analysis. You'll find what I'm going to go over, at least the blank pages of it, at the end of the complete curve analysis experiment. So why don't you turn to that now, and the title of this should be Weak Acid Strong Base Titration, the one we're going to start off with. I'd recommend that you write in your lab manual on the pages provided. While we go along, I think you'll learn the material better. The first curve we're going to start with is the titration of 75 milliliters of a weak acid, ascorbic acid, monoprotic, with 0.200 molar sodium hydroxide. And I performed this titration, and this is what the curve looks like. And we're going to analyze 4 points on this curve. Actually, we're going to do 5. And we're going to calculate the pH and the milliliters added at each point that we're going to talk about. Okay. The problem statement says there are 75 milliliters of 0.250 molar ascorbic acid as titrated with 0.200 molar sodium hydroxide. The Ka and the Kb of ascorbic acid is given. 1a asks for what is the initial pH of the acid solution prior to starting the titration. And I've marked this on the curve. There's a picture of the curve also in your laboratory manual. So we want to know the pH at the point where no sodium hydroxide has been added. The first thing you're going to need to do is write the reaction equation for the dissociation of a weak acid. Now I've written it here as ascorbic acid going to hydrogen ion, H+, and the ascorbic acid ion. But if you wanted to, you could just say HA goes to H+ plus A minus. I'm okay with that. The next thing we're going to do is to set up an ice table. So I is our initial concentration of each species in that chemical equation. We're given the initial molar concentration of ascorbic acid. So it's 0.25, and I wrote that down here. And the hydrogen ion and the anion associated with the weak acid are both going to be 0 when we start out. The change in concentration is going to be the stoichiometric multiplier. You can see that it's 1 for each species in the chemical reaction, so it's going to be x, or 1x. You're going to decrease or subtract concentrations of the reactants and increase or add concentrations of the products. Your E is your equilibrium concentration, where you're going to add the I and the C. Next, you're going to take your Ka, and you know you need to use Ka because you see H+, the hydronium ion, in the products, and you're going to set that equal to the concentration of the products multiplied together, x times x, or x squared, divided by the concentration of your reactants. You're going to solve for x. Now, something interesting that you should probably understand very early on, and that is this x right here. When you have a plus x or a minus x, for the most part, you can take that to 0. And here I've ignored it. It will end up being so small, which you can actually see that it is when you solve for this, compared to 0.25, it's of no importance in the equation. So I took that to 0, I solved for x, and then I'm going to realize that x is my hydrogen ion concentration, right here. If I take the negative log of that hydrogen ion concentration, I'm going to get a pH. Let's put that on the graph. There it is. So my initial point, where I have not added any sodium hydroxide, is 2.35. The next region we're going to talk about is the buffer region. Here, highlighted in the area in the blue bracket. And a buffer is a solution that resists changes in pH. So if you look at your graph again, you'll see we added a lot of sodium hydroxide, but the pH didn't change all that much. And a buffer is made up of a weak acid or a weak base. Here it's the weak acid because we've got the ascorbic acid and its salt. You're going to see this slide in a number of times during this presentation. And there might be a slight variation to it, but it is a basic methodology for calculating the pH at absolutely any point in the curve. So the first thing that we are going to do in this step equation, step 1, is we're going to use an ice table, and we're going to base that on the moles to find out what reacted. We're going to use the acid-base equation. Next, step 2, we'll calculate new molarity values using the total volume. Third, we'll use an ice table based on these new molarity values, and we're going to use the weak acid dissociation equation. Then we'll use the K equation and get the pH. So this is our basic methodology for calculating the pH at any point on your curve. Part B of question 1 asks to calculate the pH after the addition of 50 milliliters of 0.200 molar sodium hydroxide. So using the first step of the procedure, we're going to calculate the moles of the acid, base, and salt after the reaction. We're going to use the acid-base reaction equation. Again, you can use HA in place of ascorbic acid, since this is a monoprotic acid. And we are going to calculate the number of moles of each of the two reacting species. And the number of moles is simply the volume times the molarity. Now you can hopefully see that this is a limiting reactant problem. One of your reactants is going to run out way before the other one does, and that is sodium hydroxide. So only that amount can react. So only 0.0100 moles can react. And if you look on the product side, only 0.01 moles can be formed. Again, continuing with our ice table, we can add the initial and change concentrations to get an equilibrium concentration. And this is exactly what we would expect in a buffer. We only have the weak acid present and the salt of the weak acid. We don't have any base present at all. So we've completed the first step in our equation. Next, we're going to calculate, for step 2, the new molarity values of the acid and the salt after the reaction. So this is from the previous slide, our moles, and we know that moles divided by liters is molarity. My new total volume is the initial volume of the acid plus the volume of the base that I just added. Dividing moles by liters gives a new molarity value for the weak acid and its salt. Next, for step 3, we're going to set up an ice table with these new molarity values, and we're going to use the weak acid dissociation equation. Again, if you want to use HA for the monoprotic acid, you can. These values are from the previous slide, the weak acid and its salt. And again, I have the changes of the minus x and the 2 plus x's and my equilibrium values. Then for step 4, I'm going to use the Ka and calculate a pH. Again, the Ka hasn't changed. It is a constant for ascorbic acid. And I'm going to set it to the concentration of the products divided by the concentration of the reactants. I'm going to take the plus x and minus x terms, just those two terms, to 0, because we will find out that x is going to be so small in comparison to what it's being added or subtracted from that it's not going to make a difference in our equation, and I'm going to solve for x. Again, I'm going to realize that x is my hydrogen ion concentration from my ice table. If I take a negative log of this value, I get a pH. Alright, let's go ahead and put this one on this particular chart, and there it is, 4.15 at 50 milliliters of sodium hydroxide. Next, we're going to talk about the equivalence point. This is exactly equidistant between the two points of inflection on the sharp rise of the curve. For a monoprotic acid, there will be one equivalence point, which we see here. For a diprotic acid, there will be 2, and a triprotic, there will be 3. In lab, you'll get the chance to do titrate a triprotic acid. At the equivalence point, the moles of the acid and the moles of the base are in exact stoichiometric proportions. Here, it is 1:1. In the homework, there is one where it is not 1:1. But again, it will be in exact stoichiometric proportions at the equivalence point. No acid is present, no base is present. The only species present at the equivalence point is the salt. Again, we're going to use this 4-step methodology to calculate the pH at the equivalence point. The only change here is we're going to use a different equation when we need to use the ice table for the molarity. We're going to use the hydrolysis equation. So the first step we're going to do is use an ice table to figure out what reacted, again based on moles, using the acid-base reaction equation. Using the total volume, we are going to calculate the new molarity value for the salt. Now, using the salt hydrolysis equation, we are going to use an ice table based on molarity, then use the K equation and get a pH. Again, this is the same exact slide, same methodology. We're just going to use one different equation in one part of it. The first thing we're going to do, this is 1C, is calculate the pH at the equivalence point. We're going to first calculate how much sodium hydroxide did we need to get to the equivalence point. Well, we're going to start with the volume and the molarity, the two pieces of information we know about the acid. Using dimensional analysis, we're going to multiply by the mole ratio of sodium hydroxide to the monoprotic acid, and then we're going to divide by the molarity. We will get 93.8 milliliters, or 0.0938 liters of base required. Moving on with part D, we're going to calculate the pH at the equivalence point. We are going to use our first step, an ice moles table, to calculate the moles of acid, base, and salt present after the reaction. Now, hopefully you've realized by now that there is only one thing that should be present, and that is the salt. But we're going to confirm this. We're going to use the acid-base reaction equation, and we're going to calculate the moles of our two reacting species. Again, moles is volume times molarity, and hopefully, not surprisingly, you will see that they are equal. That is all that can react, 0.0188, and again, all that can be formed of the salt. And this is exactly what we are expecting. We don't have any acid, we don't have any base, and at the equivalence point, we only have salt. Now, we are going to calculate the new molarity value of the salt after the reaction. This is from the previous slide, the equilibrium concentration, moles, and the new volume is the molarity, the volume of the acid plus the volume of the base. So moles divided by this new total volume is the new molarity of the salt in that solution. Only the salt is present, and we have salt hydrolysis. We're going to use the salt hydrolysis equation and then calculate the pH. Hydrolysis means reacting with water. So I'm going to react my active species of the salt, the anion in this case, with water, and I get back the weak acid and the hydroxide ion. And this is what is going to give me my high pH. It's a very simple ice table because only the salt is present. Nothing else is present to begin with. You have your change of the three X's and your equilibrium concentration. The fourth and last step in this procedure is to use your K equation. I'm going to use the Kb here because I see the hydroxide ion present in the products. I'm going to set that equal to the concentration of the products divided by the concentration of the reactants. And I'm going to take that small x in the denominator to 0 and solve for x. I'm going to realize that x is my hydroxide ion concentration. And so when I take the negative log of the hydroxide ion concentration, I get a POH. And by difference from 14, my pH is 8.58. This is exactly where we would expect it. The pH of a weak acid titrated with a strong base at the equivalence point must be greater than 7. Let's go ahead and put this point on the curve. And there it is. Next, we're going to talk about the post-equivalence region. At this point, there is no acid present whatsoever. It's all been reacted. All that is in solution is the salt and the strong base. And the presence of that strong base is now going to give us the pH. Part E says calculate the pH after 120 milliliters of the 0.200 molar sodium hydroxide solution have been added. We have excess sodium hydroxide. It's a little bit simpler. We don't need to use ice tables because with a strong acid and a strong base, there are no Kas, so we don't need to use the Ka. So the first step is let's figure out how much excess sodium hydroxide is present. We added 120 milliliters and it took us 93.75, I think I have it as 93.8 elsewhere, milliliters to get to the equivalence point. So that is all reacted. Therefore, the excess is the difference, or 26.25 milliliters. We're going to calculate a moles, convert it to a molarity, then calculate a POH and a pH. Knowing my volume times my molarity is moles. This is how many moles of sodium hydroxide are present. If I divide by the new total volume, 75 plus 120 milliliters, I get a new molarity. And I can realize that this is the hydroxide ion concentration. Taking a negative log of that, I'll get a POH, and by difference from 14, I get a pH. Let's put that on the curve. There's one more interesting point. I don't believe Chang talks about this at all, but it's an excellent point to at least calculate. I've seen it on exams a number of times. The half equivalence point, where your volume is half to that of the equivalence point. At that half equivalence point, the pH is equal to the pKa. Our Ka is given, again it's a constant for a specific acid. If I take the negative log of that, I get the pH. I knew it took 93.75 milliliters to reach the equivalence point, and that was calculated in C. It will take exactly half of this, 46.9, to reach the half equivalence point. Again, I can put this pair of points, this point, on the graph, and there it is. 4.10 pH and 46.88 milliliters of sodium hydroxide for the half equivalence point. And that is it for a weak acid titrated with a strong base. If we wanted to titrate a weak base with a strong acid, we're going to get the opposite shaped curve. And that should be the next picture in your lab manual. Looking as such. This one I did methylamine titrated with hydrochloric acid. We're going to calculate 5 points on this curve too. The problem statement is 100 milliliters of 0.150 methylamine solution are titrated with 0.250 molar hydrochloric acid. And I give you the initial pH. So this one is a little bit different. It's backwards from what I asked in the first one. 1A here says calculate the Ka and the Kb of the weak base. Well, if you're given the pH, you can calculate the pOH. And I'm going to do this because I know we're in a weak base. I need to calculate hydroxide ion concentrations. 10 to the negative 2.09 gives me the hydroxide ion concentration. I am going to start off with the weak base dissociation equation. And here I like to add in the water because it just kind of helps me keep my weak base straight and that I can see the OH minus. If I react my weak base with water, because it is in a water solution, I'm going to get the cation and the hydroxide ion. And this is my weak base dissociation equation. I'm going to set up an ice table. I know my initial concentration of the weak base is 0.150. And I just calculated in the previous slide the X, or the hydroxide ion concentration. Adding these together gives my equilibrium concentration. I'm going to set that equal to a Kb because I see an OH minus in the products. I don't know what my Kb is, that's what I'm trying to find out, but I know that it's equal to my products divided by my reactants. And I get a Kb of 4.4 times 10 to the negative 4th. I can easily calculate a Ka. I know that Ka times Kb is equal to Kw, and here Kw, unless otherwise specified, is 1 times 10 to the negative 14th. We'll go ahead and put that on the curve. When I've added 0 milliliters, or no hydrochloric acid has been added, the pH is 11.91. Now we're going to calculate something in the buffer region. This very flat shaped region, again, where the pH does not change significantly. Again, this is a repeat of a previous slide. A buffer is a solution that changes very little pH-wise when you add a lot of the titrant. And here it's going to be made up of a weak base and its salt. You have seen this slide twice already. Again, we're using the same methodology. Step 1, we're going to use an ice table based on the moles to find out what reacted. And we're going to use the acid-base reaction equation. We're going to calculate, for step 2, the new molarity values with the total volume. Step 3, we're going to use an ice table with these new molarity values using the weak base dissociation equation. Then we're going to use our K equation and get a pH. Alright, 1B asks for calculate the pH after the addition of 40 milliliters of 0.250 molar hydrochloric acid. We're going to use step 1. First, calculate the moles of the acid, base, and salt present after the reaction. Here's our acid-base or base-acid reaction equation. And our moles is the volume times the molarity. And hopefully you'll recognize here that our hydrochloric acid is the limiting reagent. And all of that hydrochloric acid will react before and run out before the weak base runs out. So that is all that can react, 0.01 moles, and all that can be formed. Adding the two together, we'll get the equilibrium moles. Again, in the buffer, you can recognize the only thing present is the weak base and its salt. We've done step 1 of the procedure. Step 2, that's from the previous slide, is we're going to calculate a new total volume and new molarity values. The new total volume, I've always had 100 milliliters from the base, and I've added 40 milliliters at this point in time from the acid. Moles divided by volume will give new molarities, and I have new molarity values for the weak base and its salt. And for the third step, I'm going to use the weak base dissociation equation. And, I have a helpful hint here. Remember that the salt can dissociate into the anion and the inactive cation here. The initial concentration of the weak base and its salt is calculated from a previous slide. I have my change, the 3 x's, and the equilibrium concentration is adding the initial and the change together. Again, I'm still going to use Kb because I see OH minus in the products, and set that equal to the concentration of the products divided by the concentration of the reactants. I'm going to take the two small plus and minus x terms to 0 and solve for x, realizing that that is the hydroxide ion concentration. X is the hydroxide ion concentration. Taking the negative log of that, I get a POH, and the difference from 14 is a pH. We're going to go put this point on the graph. And that's pretty much what we would expect. I've added a lot, 40 milliliters of hydrochloric acid, and the pH has only changed by maybe 1.5, less than 2 pH units. At the equivalence point, the moles of the acid and the moles of the base are in exact stoichiometric proportions. Again, here it's 1:1. In the homework, one of the problems is not 1:1. No acid is present, no base is present, only the salt is present. And we're going to use the same 4-step methodology to calculate the pH. Ice table using moles to determine what reacted, using the acid-base equation. Calculate a new molarity for the salt with the total volume. Use the salt hydrolysis equation and set up an ice table based on these new molarity values. Use your K and a pH. So in part, I guess we're in part 2C. I don't know why it says 1 again. please excuse that. I will change that in the lab manual. First, calculate the milliliters of the hydrochloric acid required to reach the equivalence point. Starting with the volume and the molarity of the base, using a mole ratio from my acid to my base and dividing by the molarity of the acid, I get that 60 milliliters, 0.0600 liters, are required to reach the equivalence point. Next, in part D, we're going to calculate the moles of the acid, base, and the salt after the reaction, or step 1 of the procedure. There's our base plus an acid, gives you a salt and water equation. I'm calculating new moles, volume times molarity, for both reactants. And we know we're at the equivalence point because stoichiometrically they are equal. That's all that can react and be formed for the salt, and that is the only thing that is left in solution. We finished step 1 of the procedure. Step 2 of the procedure, we're going to repeat this slide, part of this slide here, is let's calculate new molarity values. Our total volume is 100 milliliters of the base and 60 of the acid. So moles divided by volume is molarity. That's step 2 of the procedure. Now only the salt is present. And we have salt hydrolysis, the wake me up slide. And we're going to use the salt hydrolysis equation to get our new molar values, and we're going to calculate the pH. So salt hydrolysis is your active part, your cation of the base, reacting with water, and I get back the weak base and also the hydronium or H+ ion. Again, at the equivalence point, this molarity table is a very simple molarity table. The only thing present is the salt. You've got your 3 x's, the changes, and your equilibrium value. We're going to set this equal to the Ka now because we see H+ in the products. And that's equal to the concentration of the products divided by the concentration of the reactants, taking that minus x to 0 and solve for x. I'm going to realize x is my hydrogen ion concentration. So if I take the negative log of that, I get a pH. Now this is going to make a lot of sense because my pH of the equivalence point of a weak base titrated with a strong acid should be less than 7. I'll repeat again, a strong acid with a weak base is less than 7. A strong base with a weak acid, like we did prior, is greater than 7. And at the equivalence point of a strong acid and a strong base is equal to exactly 7. You'll get this in the lab. I don't care what it looks like when you plot it. The pH of a strong acid, strong base titration, the equivalence point, is equal to 7. So that will be in the lab. Next, we've got our post-equivalence region, and this is part E, after 100 milliliters of the acid have been added. Again, we do not need an ice table because really the only thing that is present in great excess that's giving us the pH is a strong acid which does not have a Ka. We're going to calculate how much hydrochloric acid is in excess. We added 100 milliliters. We took 60, reacted 60 to the equivalence point, so I've got an excess of 40. I'm going to calculate the moles, convert it to a molarity, and calculate a pH. The volume of excess times the molarity gives me my moles, and the moles divided by the total volume, 0.2 liters now, gives me a new molarity for the acid. This is also equal to the hydrogen ion concentration. I'm going to take a negative log of that and get a pH. And I can put this also on the curve. Again, there's one more point that we're going to put on this curve. It's the half equivalence point, when exactly half of the moles of the base have reacted and half of the milliliters of acid needed to reach that endpoint are added. And here again, at the half equivalence point, the pH is equal to the pKa, or the pOH is equal to the pKb. The Ka we calculated back in part A is 2.3 times 10 to the negative 11th, and I take the negative log of that to get a pH. Since it took 60 to reach the equivalence point, it will take half of this, 30, to reach the half equivalence point. So I can put the pair 30 and 10.64 on the curve. And there it is. We've calculated 5 points for this curve. So with this, you can calculate any point on an acid-base titration curve using your methodology, your 4-step methodology, and also knowing exactly where you are on the curve, whether you're in the post-equivalence region and may not have to use it, or a modified formula of that. You can calculate any point, pH, on any curve in an acid-base titration equation. Thank you all for listening, and I hope you all have a great, great day.